So hello everyone, let me briefly introduce myself. I am Samyukta Indrasena. I'm a researcher at Fortiss Research Institute in Munich, Germany. And here at Fortiss, we mostly work towards software intensive systems. We work at the collaboration with various industries like AI, sorry, one second, yes, AI, industrial IoT, robotics, and mainly software solutions. So, and today it gives me immense pleasure to be coordinating this session. I'd like to also convey my the apologies from Dr. Rute Sofia because of personal reasons she couldn't be here, as well as Professor Dr. Ramji Prasad. But as we are speaking here, he's being honored for his work and also receiving an award. So I'd like to also begin with briefly introducing CONASENSE as a community for people who are new here. It's an international initiative where we work towards not only wireless communication systems alone, but also towards communication, sensing, AI, navigation, sustainability, and human-centric services. And we are delighted to have a first session with all of you present here. Yes, and today's session, the 6G and beyond, is one of the most interesting topics, and where we'll also be covering about the quantum communications journal. So we'll briefly go through all of the other events as well. We have our upcoming events, which will also uh, include the Connaissance brainstorming event, the energy efficiency workshop that will happen in October. And for all of you all who are interested, please contact us at Fortress, contact Professor Dr. Rutsi Sofia. And for our agenda today, without I think much ado, I will pass the floor to Paulo, who is also the editor-in-chief for the Quantum Communications magazine. So I think I hand over the floor to you, Paulo.
It's a pleasure being here. Thank you for the introduction. Good afternoon, everyone. Can you see the presentation here? In this world, today I'm pleased to present the Quantum Information Technologies Journal, also known as QITJ. This is an open access journal created by River Publishers together with the CONASENSE platform. The journal is designed to become a dedicated space for quantum research, industrial innovation, and applied technologies. And its mission is to connect scientific knowledge with real-world applications and to support global development of quantum technologies. Now, as you can see, the Quantum Information Technologies Journal is a platform for publishing cutting-edge research and industrial development in quantum technologies. Now, we just published the first edition, which has access online and also a ISSN register. And the first edition, as I said, was released in 2025 in December, and we are now preparing for the second edition. All of you are invited to join us and submit your topics, and it's going through a peer review. And they are becoming relevant. The journal is becoming relevant to communications, cybersecurity, sensing, healthcare, finance, logistics, energy, and many other sectors that apply quantum technologies. Here is just a brief overview of the aim and scope of the journal. The scope of QITJ covers the main areas of the quantum technology landscape. This includes quantum computing, such as algorithms, hardware, simulations, and quantum machine learning. It also includes quantum communications, networking, and cryptography, including quantum key distribution, post-quantum security systems. Also, the journal welcomes work in quantum information theory, quantum sensing, industrial applications, and quantum standardization. This broad scope allows the journal to bring together different communities that are often working separately. The editorial leadership and ecosystem. I'm pleased here to be with my colleagues and the professors here, Professor Casey, Professor Alberto Comin also. Both of them will introduce themselves later. But QETG is supported by an international editorial team. And the editors-in-chief, as I said, already mentioned, and Professor Kwang-Cheng from the University of South Florida, who is the speaker right after me. Myself, Paulo Henrique from CTF Global Capsule and River Publishers. And the editorial board includes experts from organizations such as Airbus, Albert Coming is here, Intel, and St. Jude Research Hospital. The journal is also connected to the CONASENSE steering committee, which includes Professor Rute, Sofia, and Professor Ranj Prasad. This combination of academic, industrial, institutional experience gives the journal a strong foundation. One of the key missions of the Quantum Information Technology Journal is to build a bridge between academia and industry. On one side, we have research theory, educations, like here we have the presence of Vanessa Muhani, so she also is educational outreach from Spark Photonics. She will speak, she also published with us, and scientific discovery. On the other side, we have industrial deployment, commercial applications, and real-world challenges applications and discussions. The key ITG aims to connect both sides by publishing not only scientific papers, but also industrial case studies, application-driven research, and contributions that support quantum education and workforce development. Just here showing to you, we've been covering the industrial conferences in quantum, and the latest one, there are two. This is, you're gonna have access to this presentation. They have a link if you click to our podcast. The interview with Thierry Bautier, which is the Executive Director of QUIC, the European Quantum Industry Consortium, and Dr. Alejandro Henrique, Head of Quantum BW, a quantum institution in Germany fostering quantum application services, and many others. And new videos of our podcast will come up, because 2 weeks ago also was covering the ETSI quantum cryptography standardization in Canada. More is to come. You're gonna see all of these podcasts also in the River Publishers YouTube channel. Finally, as I said, the Quantum Information Technology Journal, it's a fully open access journal, which means that published articles can be accessed by readers worldwide. Articles are published under a Creative Commons license, allowing the work to be shared with proper attributions for non-commercial purpose. Also, authors can deposit published versions in institutional repositories. This is an open model. It's important because quantum technologies are developing globally, and broad access to knowledge helps accelerate the collaboration, education, and innovation. In terms of the inaugural edition, just a few highlights here that I want to bring to you. This is the highlight, the edition, it's available. You're going to see in the QR code later. You can access. We had the editorial board, which was comprised by the words of Professor Rute, Sofia, and Professor Ranj Prasad. So we had also an article, Quantum in a Classroom. Vanessa is here, she will highlight more about that. The Quantum Communication Frontier, also from Airbus, from the scientist Paulo Mendes. Post-quantum cryptography, Michael Fazzulo, who is located in the Silicon Valley. Quantum computing standardization and regulation from Valerio Frescola from Intel. A quantized history of quantum mechanics and quantum for quantum engineers. This is an outlook from the workshop I delivered at IEEE in Princeton, and a hybrid quantum security integration of QKD and PQC in the brownfield optical networks provided by Albert Comin, who is also a speaker today, a member of the editorial board. In terms of analytics of the KITJ based on the first edition, so just to highlight, we had 7 articles tracked, total interactions 1,406. In terms of readings, just in abstracts were 745. And the top article by total interactions was the one provided by Valerio Frescola. The first edition also shows encouraging engagement across the track articles. The journal has recorded strong levels of interactions, including, as I said, abstract views, PDF views, HTML views, and the article Quantum Computer Standardization and Regulation showed the highest total engagement, followed by strong performance from article on quantum communications, post-quantum cryptography, and hybrid quantum security. Now, in terms of reader engagement, to give some patterns to you, the engagement data shows that readers are interacting with the journal in different ways. Some readers, they begin with the abstract, while others go direct to the PDF format of the articles or the HTML version of the article. This is a positive because it shows both discovery and deeper reading. For a new journal, this is a type of engagement that is important to us, as it confirms that the content is attracting attention from different audiences, including researchers, practitioners, and technologies stakeholders. Now, as we are gearing up to the second edition, looking ahead, KITJ is now preparing it to consolidate its second edition. The call for paper, the deadline is 31st of July. The goal is to attract high quality contributions from researchers, industry professionals, and institutions working across the quantum technology value chain. And we are particularly interested in papers that connect theory with applications, including quantum computing, communications, quantum sense and metrology, cryptography, industrial use cases, in standardizations, and quantum education. We invite the wider quantum community to submit papers, collaborate, and help shape the QITJ as a global platform for our quantum innovation. This is our ambition and our goal. Thank you very much. Thank you for your attention. For submissions and collaborations and further information about the KITJ, please access our website. You will get to know more details, and the presentation will be here made available to you right after. Thank you. Samyutka, it's over to you.
We have next Professor Kwang-Cheng from the University of South Florida, who's also the editorial chief for the Quantum Technologies magazine. We welcome you, Professor, and the floor is yours.
Okay. Okay, so the first of all, thank you for these great opportunities. Thank the chairwoman, and also for everyone. This is a great opportunities for me to give the talk, and particularly follow the outstanding presentation by Paulo. And please support the journal as possible as you can. And today I was suggest to give the talk about the quantum information technologies as the foundation for future communications. And in terms of the quantum technology, this is really suggests a kind of revolutionary engineering paradigms. And so you probably can see my photo with the quantum computers, and that's very shining. But let me first introduce everyone. Probably remember in 2022, the 3 persons shared the Nobel Prize in the physics, and I believe this person also actually spent lots of the effort to build up the quantum the remote quantum key distributions. Last years we also have the Nobel Prize in physics that will be contribute to quantum computing and also quantum technology, and also the semiconductor technologies. So today I'm trying to look into something from a slightly different angle because in the past people are always talking about the quantum information science, but we already know quantum technology is kind of the game changers, and so this will be a kind of the new landscape for the future technology. But this is the time we want to migrate from the quantum information sciences to quantum information engineering. So this is a really the time from the science to engineers, and that makes everything, makes something happen. But the first thing is, let me first look into the hot subject. There are many people working on the quantum key distributions, and then what's the relationship with the communication. But if we look at the left hand left hand side, this is actually a kind of secure communication by the cryptography. This is a pretty classical communications. So we have the Alice and Bob, and then we have some kind of the key management, and such that Alice and Bob can share the key and to reach the communications. According to channel information theory, the key length must be larger than the size of the message. And so in that case, the perfect security can be done by the one-time pad. And that is probably the most secure mechanism for the one-time pad. The only problem is the key distribution is kind of troubled. So at the right-hand side, we can see the quantum key distributions. So basically, Alice and Bob, they try to using the quantum channels, and the if can try to is dropping from the in the middle. But in the meantime, there's a hidden assumptions for quantum key distribution, which means there is an authentication channel, which is reliable, provide a reliable communication between Alice and Bob. And so in this case, once we provide the key, it's actually a good supplementary functions for traditional secure communication by cryptography. So therefore, I always try to remind everyone, yes, the quantum key distributions leverage the property of quantum mechanics, but on the other way is this is actually for the classical secure communication and therefore the networking. And also the quantum key distribution, because it just shares the key. So it does not involve the information transmission through the quantum channel. So in this case, this is not really a kind of the quantum communications, but however, that will be definitely related to the technology itself. In terms of the quantum communication technology, there will be two categories. The first category I call is a quantum classical communications. The main idea is try to transmit the classical informations over the quantum channels. So you can see from the figures. So we have the classical source for the informations, and then Alice need to have the quantum encoder to map the classical message into the quantum state. If the quantum state will be the pure state, and of course that will be gamma A, the kit gamma A. If that will be the mixed state, and in the more general sense, and there will be the density operator will be the rho A. And going through the quantum channel, there will be some kind of the noise and distortions, and therefore we are going to have the rho A hat as the new receive the density operators. And Bob need to provide the quantum measurement, and after the quantum measurement and make the decision, and such that can try to recover the original message A hat. So this is the quantum classical communications. So that means, let me repeat again. So we transmit the classical information over the quantum channels. One of the key issue here is how can we have the quantum encoders, and how can we conduct the quantum measurement? And the quantum measurement usually involves selecting a kind of the projection operators, PK, and then this is generally involves so-called the POVM, positive operator value measure. And the entire theory is actually a very interesting construct by the John von Neumann. That would be the person who invented the computers. One big problem here is, of course, how can we embed it, the classical meshing into the quantum encoder, and how can we encode the classical meshings into the quantum states? As everyone knows, the single qubit quantum state can be represented by the so-called the Black sphere as the left-hand side, and typically we are using the z-axis, and that means the k0 and the k1. And the diagonal one for the axis, that will be diagonal A and diagonal the kid A and kid D. So in quantum machine learning, there will be a technology called the quantum embeddings that is also known as a quantum feature map. This is actually try to achieve something similar. How can we embed the classical data onto the block field? And in this case, the quantum signal detections, there will be a kind of the classification problem. So I suggest by the papers, if you see these archive numbers by Professor Lloyd at MIT, and it actually suggests if the quantum embedding or the quantum encoders has been appropriately designed, therefore the quantum classification, so which means the detection of the quantum signal, will be rather trivial. And another class of the quantum communication would be entangle-based quantum communications. At the right-hand side, you probably see the movie and also the TV series about the Star Trek, and there are lots of the scheme about the teleportations. In Actually, it is indeed possible to teleport for quantum teleportations. The operation of quantum teleportation we can see at the left-hand side. So the purpose is try to teleport the quantum state by Alice and to Bob. So therefore Bob can recover the teleported quantum state. The trick is actually go this way. So we are actually using the quantum entanglement. The quantum entanglement, this is so-called the entanglement source or the EPR source. So basically, we try to create the bare state, and the bare state is actually a pair of the entangled photons or entangled particles. So these two particles, entangled particles, one sent to Alice, another one to Bob. Okay, so in this case, Alice have two particles, his original quantum state to quantum teleport, and the other one is from the entangled source. So what Alice is going to do is he's going to do the joint measurements, bare state measurement, and then try to identify four possibilities because there will be two particles. And based on these four possibilities, 0, 0, 0, 1, 1, 0, and 1, 1, and he sent this measurement outcome to Bob through some kind of the classical channel. So based on the classical information about the measurement outcome, and then Bob can actually using this entangled photon to reconstruct the original quantum state by Alice. Okay, so this is something very interesting. Please remember, when Alice took the quantum measurements, during quantum measurement, the original quantum state already collapsed. Just remember, once we measure the quantum state, and that quantum state going to collapse. So in this case, the quantum state information already gone. It actually does not exist in the world at this time. Okay, so this is the time nexus at this time. But after some classical information about the outcome, Bob can leverage the entangled photon to reconstruct, construct the original state of the Alice. So this is something very amazing. But in terms of mathematics, it's not particularly complex, like a 1-2 page derivation, and you are going to get it. And so this is a very amazing result. It's known as the quantum teleportations. So people are going to argue, is that the speed of communication, quantum teleportation, faster than the speed of light? The answer is no, because from A to B, Alice to Bob, is rely on the classical communication channels. So based on this, the quantum teleportation, and then we may know something interesting. The reason is for this entanglement source to send the entangled photon to Alice and to Bob. In this case, these two channels are likely to be identical or even to be balanced. Okay, so then I asked my student, well, if the channel would not be balanced, what's going to happen? So then once in this situation, we find something very interesting at the right-hand side. So if that would be the imbalanced quantum channel, and the deep blue, which means the channels, the array is actually in good conditions. Once go into the bright colors, which means probably the error will be very high. So you can see as long as the two channels are balanced, and then the quantum interpretation will be good. Otherwise, that will be kind of the trouble. And there'll be even more complicated behavior from this imbalance. And this imbalance is actually, if we look into the quantum swap, the quantum swap is actually by the two quantum teleportations. And so there'll be AB and the CD. So if the BC, we call the quantum repeater node, take the joint measurement, and then in this case, A and D will be entangled. So the entangled information will be transported from A to D, although the A to D never communicate directly to each other. So this is another amazing part. It's called the quantum repeaters, and based on the quantum swap, and this is further based on the quantum teleportations. So then we can look into the behavior. That's really kind of weird because there's only some kind of the tiny portion with the deep blue and in the corner and otherwise, and this is actually pretty yellow, which means the error rate will be pretty high. So this kind of imbalance situations, we actually publish the paper, present the paper in last year's WPMC just half a year ago. And another way we can use in the quantum technology to help communication. I put down one example. The example is everyone know about the radio resource problem, allocation problem in wireless communications. And the resource allocation pretty much in general is a knapsack problem. And this is very desired to solve. And this is actually well known as a kind of the computational hard problem. But in the resource allocation in real communication, particularly when there are a huge number of the user, and then there will be multiple frequency band, and so they will become a kind of computational hungry problem. So is that possible? We can use quantum computing to solve the problem. The answer is yes, because this radio resource allocation problem is actually the resource allocation problem. We can transfer it into so-called the quadratic unconstrained binary optimization QUBO problem. And this is already proved to be a class of the NP-hard problem. So that we can have this kind of the object functions, and then subject to the binary combination, subject to the number of the end users. Traditionally, we try if the n is very large. If they'll be small, of course, we can use the classical computer to compute. But if the n is really large, and then we're going to using the scientific annealing, which is based on statistical physics to finish the job. And is that possible? We can use quantum annealing, and so-called the quantum optimization techniques. The answer is yes, and actually we already demonstrate we can use a quantum approximate optimization algorithm called the QAOA. This is like the archive papers 12 years ago, but widely accepted. I'm not sure the numbers, quite a few thousands or even like 10,000 citations within these years. And but this problem is not as simple as it appears. The reason is if we have the radio resource problem, we have lots of the boundary constraint, and then that actually create lots of the complexity for the quantum computation and quantum optimizations. So it turned out we have to be very careful in terms of the quantum state preparations, and to use the minimum number of the qubit, and then we have to leverage the conflict graphs and the graph theories to help us to formulate the problem. And finally, we conduct the quantum local search. And in this way, we can facilitate the qubit efficient computations. And this is actually the work just published in the IEEE JSEC 2026, actually just a few weeks ago. This is a good example, although it's never been trivial, and to develop the efficient quantum computation to solve the problem. And one of the reasons is that today's quantum computers actually have very low efficiency, and which means there'll be probably only 10% or no more than 20% of the qubit can really contribute to the computations. And the rest of the problem is about the measurement of the outcome. And please remember, if we try to measure the quantum state, what we really get is a kind of probability distribution to several possibilities. So which means we need to repeat a good number of times. Typically, if you play around the quiz kit, and you probably have to repeat, ask the quiz kit to repeat 1,000 times to really get the distribution, probability distribution for the outcome. And so we have the another question is, can we do it in an efficient way? And so this, we developed the technology so-called adaptive QST. And so we published the papers, original idea in 2024 WPMC, and then we further developed the some hardware implementation in 2025 WPMC. And right now it's revised for the Prestigious IEEE journal. And so this is very important because the efficient quantum measurement, or the other way is quantum state tomography, is actually so needed to enhance the efficiency of quantum communication and computing. So by this way, we can actually reduce the repetition from 1,000 drop to around a little bit over the 100 to 200 range, and so that is actually significantly increase the efficiency. And I want to use the some final a few slides and try to conclude what will be the technical challenge of the quantum communication from what we can see. The first is no matter we are using optical fiber, we are using the wireless quantum wireless communications. The quantum entanglement typically involves only the single pair of the photons. So this is very sensitive because a single photon can be easily absorbed by the environment. And so that would be the first challenge. The second challenge is what would be the efficient quantum signaling and therefore the error correction or the error mitigation techniques. So this is one situation I have to remind. The quantum computer is actually a so-called quantum closed systems. So it's actually closed, don't interact with outside. But quantum communication system in general, they are quantum open system, which means it's going to interact with outside and therefore it's going to significantly influence about the performance. So this is an even harder problem. So quantum communication is much harder than the quantum computing. And we also have the quantum source encoder and decoder, as we just mentioned. And another issue I want to remind is in classical communication, we get used to the signal processing for the receiver. But quantum signal processing is difficult, if not possible. Okay. One of the reasons you can consider is there's no quantum memory available at this time. And the part of the reason is the quantum no current theorems. So which means quantum no current theorem, which say that if we have the arbitrary quantum state and there's no way we can copy it. So therefore, the memory in general is always kind of challenge. And finally, the quantum communication usually secure, but it's very low rate communications. So how to achieve the reliable high rate communications, and that with the efficient quantum measurement process, that is always kind of trouble. So at the right hand side, you can see the quantum decoherence. Once we have the open systems, let's say the original quantum state is here, and then it's going to degenerate, and then this is the quantum decoherence process. And the further is that how can we implement the quantum circuits? And it's well known if we for the quantum computing in order to keep the entanglement. So we are going to put the quantum computer in the refrigerators. But in quantum communication, it's open system, so therefore it's very difficult. So we have to adopt lots of the room temperature quantum techniques. The typical ways, for example, like quantum photonics, and that's actually quite different from the quantum computers. The quantum computers using the superconductings. This require almost 0 degree K, and we're using the trap iron, neutral atom, and this typically also operate in the low temperatures. And the quantum photonics, of course, can operate at the room temperatures. So these are also quite widely considered in quantum computers, but how to apply into develop the quantum circuitry for the quantum communication, that will be the interesting part. So at the right hand side, you can see this is the photo from the Senate, and they're showing the integrated photonics, quantum photonics. And finally, the quantum communication can contribute to another important computing problem, that is distributed quantum computing. So after the introduce, I would say just like a stupid bird to fly first and try to introduce some kind of the communications and the quantum techniques that will be helpful for the future quantum communications. And I hope someday in the future, in the near future, we are going to have the quantum-centric communications. So thank you very much. And any questions? And this is a photo I took in Japan. So it's like the big trees. There's the small temple under the big trees. The big trees probably those are Nobel laureate in the physics, and then we are engineers. We just starting something meaningful. Thank you very much.
Thank you very much, Professor Kwang-Cheng. It was a very inspiring presentation. You've shown us how information technologies are not just evolving from fundamental sciences, but also contributing towards future communication systems. Building on that foundation, our next speaker we have with us is Dr. Alberto Cormin from Airbus Germany, who will be sharing us an industry perspective of quantum communications. And he's also the editorial board member of the Quantum Communications magazine. Dr. Alberto, the floor is yours.
Yet.
Yes, we can see it. Yes.
Yeah, okay, great. All right. It will be an easier presentation than Professor Wang before. I will tackle more from an Airbus perspective. We have been working on QKD and quantum network since a few years. I will share perspective on challenges on how to bring QKD to a deployable system. Perhaps the content will sound a bit easy after this presentation, but just quite a reminder of what. Can you still see my presentation? Sorry, because I don't see it in my.
Yes, we can see it.
Okay, good. Okay, so what is a quantum key distribution and what is not a quantum key distribution? What is a physics-based method for sharing keys for symmetric cryptography. That's important. Many people complain about QKD or think it is basically not useful, but maybe they often misunderstand it as a universal toolbox. They want to replace traditional cryptography, which is not the case. It is a point-to-point technique, so it's not allowing you to share keys between arbitrary nodes in a network by itself, at least natively. And most notably, it does not provide authentication. So if Alice and Bob never met before, they don't have any way to use QKD to share a secret. And this can be mitigated in several ways, for example, by combining QKD with traditional cryptography, for example, with EQC, post-quantum cryptography, and using post-quantum cryptography to authenticate the channels, and then using QKD to share an encryption key. Or you can simply pre-install in a secure way some shared secret in the two nodes and then use it for digital authentication. QKD is also not an arbitrary range technique, as Professor Chen showed before, mainly because you are sending quantum states and you cannot amplify or copy them. And therefore, when you have, for example, scattering in an optical fiber, or when you have dispersion or your free space beam spread in space, then you losing signal and you have encounter severe range limitation. Now, unfortunately, most of the business value in QKD does not lie in connecting pairs of nodes. You really unlock the business value when you have a network and you can share keys between arbitrary nodes, for example. And you see here a very simple example. You have Alice, Charlie, and Bob, 3 nodes network. Alice and Bob share a quantum channel. Charlie and Bob share a quantum channel. Quantum channel has a precise mathematical definition, of course, but in a simple terms means you can send a quantum state and recover the quantum state with high fidelity. So how Alice can then send a quantum state to Bob without having a direct link? There are several ways. Ideally, you would perform, for example, a routing. You could potentially send a quantum state from Alice to Charlie. Charlie could store it in a quantum memory, for example, perhaps applying some quantum error correction, and maybe forward to Bob. Okay. But this goes a bit beyond what is currently possible, and perhaps not even what you want. What it's currently done is that in the central node, we call it Charlie, you have 2 pairs of QKD devices. You have one link which connects Alice to Charlie, a pair of QKD transmitter and QKD receiver, and one pair of devices, another transmitter and receiver, which connects Charlie and Bob. And now what you can do, you can use one of the 2 links to encrypt a message, for example, or a key that you want to relay, send it from Alice and Charlie, de-encode, and then re-encode the key again and send it to Bob. This has the obvious shortcoming that Charlie ends up knowing all the secret information that Alice and Bob want to exchange between each other. And that's the reason why it is called trusted node. So a bit more into detail how this works, I will show you a very simple sketch on how a QKD network works. This is being formalized in a document by the ITU about 2019, so 7 years ago. And it is an architecture which allows to share and to route encryption keys in a network using trusted nodes. So here again, I show an example of 3 nodes, Alice and Bob. Alice and Charlie in the middle, they share a QKD link, which allows them to share, to obtain a shared key, is a white key. And Bob and Charlie share yet a black key. So Alice and Bob currently do not have any shared keys. Another important device in a network is the key management system. Typically, each node has its own KMS, key management system. This has 2 functionalities, several, but 2 main ones are to store the keys in a secure vault, for example, and to route the keys. So the KMS, they are connected to each other. That's also called sometimes a QNL, quantum networking layer. It is also a classical link. What this link allows to do is to share information between the KMS and eventually to route a session key from the first node to the end node. How this is done, you typically encrypt this golden key with the white key using the one-time pad, for example. Mathematically, it's a XOR operation. You send the XOR key from Alice to Charlie in the middle. Charlie uses its white key to decrypt the session key. So you can read the session key. You can re-encrypt the key using the black key, send it to Bob. Bob will decrypt it and send it to the key management system of Bob. In this way, when you have an application on both sides, the application can retrieve the session keys from their KMS in a transparent way without having to care about the detail of the key routing and transport layer. Overall, the network can be managed in several ways. Perhaps the most common way is to mimic our 5G or 6G network is managed using a software-defined network controller, which can then determine the optimal path to route the keys across the network, depending on the condition of the links, for example, dynamically. You can also have another situation in which you have many controllers. Eventually, you can also have one controller for each node. And then in a distributed network scenario, you have each node exploring its surrounding and getting a knowledge of the network and routing the key. This is how currently the network operates. And how fundamentally a local metropolitan network will operate. However, we still have two fundamental limitations. And one limitation is that quantum states are fragile. They are difficult to transport. In fibers, you can transport a photon for a maximum of 100 kilometers. That's what you get because of the impurities in the silicon fibers and the scattering. Because of scattering, and you also have an exponential link loss. This can be mitigated, for example, using the free space links, for example, satellite links. And the reason is that in free space, the link loss scales quadratically instead of exponentially. In this way, you can share keys between locations separated by thousands of kilometers of distance. And another option that I don't need to go into detail because it was very well explained in the previous talk is to use untrusted quantum relays. These are the famous quantum repeaters. In this case, Alice and a relay share a pair of entangled photons, and then the relay does a joint measurement, like a Bell measurement, and by projecting these two states into a Bell state, can establish entanglement between the state in Alice and the state of the second relay. A quality relay because these nodes do not need to be trusted. So fundamentally, you can extend the range between Alice and Bob without introducing any untrusted nodes. That being said, the technology for quantum repeaters is a bit far away into the future, mainly because if you implemented it like this, simply doing Bell measurement on the nodes, and without doing any action, without using any quantum memories, it will be extremely inefficient. And for implementing a usable and efficient quantum repeater, you will need fundamentally quantum memories with much better performance than you have today. What we do in Airbus, we focus on the free space components, mainly because of our company heritage. In Airbus, we can provide fundamentally all the components from system level to subsystem to even component level of a space-to-ground QKD. Typically, in a space-based QKD, you have three segments. You have a space segment, the satellite, you have a user segment, and also you have a ground segment, which controls the link. Airbus can provide the satellites, can provide the telescopes, can provide also the optical bench and even the quantum terminal, thanks to its subsidiaries, TESAT, for example. Can provide the ground segment basically the ground stations, and also some layers of the terrestrial network management. That's a bit of history of Airbus and the current situation. We did some experiment in the past. We implemented some test benches. Here is the first one we did on the optical table. You have everything classical link, optical link. This was a BB84 protocol to implement the QKD with a key rate of a few kilobit per second of security rate. We then did other tests over longer distances, up to 3 kilometers locally. And then it is a few sketches of further technologies in Airbus. We also participated in some of the architectural studies for the future EuroQCI, which, as you know, is the future European quantum communication infrastructure. And we are also participating as an associated partner in the German QCI, where we work on a free space link between the Airbus site and the site of German Armed Forces University. Okay. So to summarize this brief talk, what is QKD today? Today, QKD is a technique which can be networked to route encryption keys in a network. It has mainly niche use cases. First customers are government and the military. The focus today regarding QKD is on certification, mainly. The reason is that QKD was developed in academia using, let's say, a security proof, which have a very high mathematical validity, but to be developed further and to be viable for government and military use, they need to have, let's say, a more detailed and hardware-specific security proof. In the future, as was already mentioned in the previous talk, the outlook is to go beyond the QKD, to have a network where you can not only route quantum states between one device and the other device, but where you can also route entanglement. And by routing entanglement means you can have a shared of pairs of entangled qubit shared between the two quantum processors or two quantum sensors. Then the network becomes a way to manage and distribute entanglement as a resource. And once you can distribute entanglement, you can unlock applications such as distributed quantum computing, distributed quantum sensing, for example, or even blind quantum computing, where you can think of having an application running on sensitive data, for example, sensitive financial data or sensitive health data, and running it on a remote quantum computer without sharing with the provider of the quantum computer any data, or even without sharing which type of problems you're working on. That's the outlook. But currently we are focusing at least at the corporate level on quantum key distribution with trusted nodes. And with this, I will conclude my presentation, and thank you for your attention.
Very much, Alberto, for the excellent presentation. We've seen how quantum tech communications are not just like evolving from point-to-point links to interconnected terrestrial as well as satellite networks, and how industry is also progressing with it. But I think building these technologies requires more than just infrastructures, and but also like people, and in the next generation of scientists, engineers, and educators. With that, we come to the final presentation of today's session. It's my pleasure to introduce to you all Vanessa Mahoney, who is an educational outreach manager at Sparks Photonics Foundation. She brings over 15 years of experience as an educator and now leads the educational outreach program. So, Vanessa, the floor is yours.
Thank you. Just going to share my
Would
screen. Welcome, everyone. Thank you so much for joining me today. I am here to present about our paper, Quantum in the Classroom, a project-based approach to building awareness. Today, I'm going to explore a structured pathway for integrating emerging technology, specifically quantum, directly into early education environments. So I wanted to give you a little bit of a background about the Spark Photonics Foundation. We're the team that actually developed the programming and wrote the paper behind it. Our core mission is to expand equitable access to high-tech career pathways. We accomplish this by embedding industry-focused STEM education into K-12 and early college, also known as K-14, engaging students long before they reach post-secondary education. So why is early intervention critical? Because the industry is facing a massive pipeline bottleneck. The vast majority of students have zero exposure to advanced technologies like quantum or semiconductors until late college or graduate school. This late exposure contributes directly to an ongoing workforce shortage. We need to build awareness much earlier. In fact, I hadn't even heard of quantum or photonics or semiconductors until I got this job a few years ago. So. To give you a little bit of background about me, my name is Vanessa Mahoney. I am the Educational Outreach Manager for the Spark Photonics Foundation. Before stepping into this role, I spent 15 years as a public school math teacher in Massachusetts. This gives me the unique background to be able to understand the massive structural constraints and time limitations in K-12 classrooms. This heavily informed our curriculum design, ensuring it is a completely turnkey, plug-and-play solution for teachers. So we tackle this problem of early awareness directly with our Spark Alpha Explore program. This initiative began in 2021 as a direct-to-student outreach pilot, but to achieve systemic scale, we transitioned to a train-the-teacher model by 2023. This puts teachers in the driver's seat and allows them to implement the program in a way that makes sense for their classroom and their students. Rather than demanding schools create a standalone heavy advanced physics class, this program integrates seamlessly into existing science, engineering, business, and entrepreneurship classes. It introduces advanced concepts through project-based learning. So let's take a look at phase 1 of the Spark Alpha Explore project. This is problem identification, where the quantum information science extension layers into the workflow. Traditionally, students work together in groups to identify a real-world problem that is personally significant to them, brainstorming any issue they are passionate about solving. The core challenge is finding a problem that can be addressed by a photonic device capable of sensing. Because quantum sensing is used specifically to achieve extreme precision, we use case stories to help students get started. These short narratives introduce real-world measurement challenges, explain why current technology falls short, and highlights real engineering constraints to give student groups a concrete launching pad. In phase 2, students transition into engineering and product development by creating their device block diagrams. Right before this phase in Spark Alpha Explore, Quantum Impact, we introduce a short hook video to kickstart their design choices. This approachable intro shows how quantum sensors detect subtle environmental changes that classical sensors miss, expanding the technological options students have in mind. From there, student groups analyze and compare 2 distinct pathways: photonic sensing, which uses light to measure things like temperature or pressure, versus quantum sensing, which uses advanced states like superposition and entanglement for extreme accuracy. To choose, students act like real engineers and utilize a decision matrix. They score both technologies against 3 strict criteria: sensitivity, cost, and need for accuracy. This activity forces them to evaluate real engineering trade-offs, justify their final technology choice, and make informed design decisions. During phase 3, students pivot from engineers to entrepreneurs as they develop a business plan covering their target market, value proposition, manufacturing logistics, and financials. We designed this phase to scale seamlessly across different grade levels. For younger learners, the financial piece is kept basic, focusing on finding a target selling price so their company can make a profit. For older learners, the complexity steps up. They calculate projected revenue, profit, and gross profit margin. Ultimately, this teaches them how to translate highly technical data into a consumer value proposition. The project culminates in the final pitch, where teams present their products and business models to a panel of judges. This is actually a fantastic place for industry and higher education professionals to get involved. For the students, it's a huge milestone. It builds crucial public speaking confidence and really reinforces their identity as real-world innovators. So running parallel to these project phases is ongoing education and industry exploration. We highly encourage teachers to bring their students on field trips to local education and industry partners. It's a great way for students to learn firsthand about the different education and career pathways available to them. To make this structured timeline completely turnkey for teachers, the Foundation provides comprehensive classroom-ready resources. As you can see, this includes digital student workbooks, structured teacher manuals, industry-modeled case stories to anchor student prompts, and templates for certificates and final pitch programs. This addresses the lack of preparatory time that stops teachers from adopting advanced STEM topics. Additionally, a curriculum cannot succeed in isolation. It requires a strong educator ecosystem. We support our teachers through a digital community of practice. This network breaks isolation by giving educators direct access to Foundation employees, targeted training modules, live digital professional development events, and a collaborative community of peers across school districts. So I already talked about the quantum impact extension to Spark Alpha Explore, but it's important to note that we've developed a suite of free resources to introduce students to quantum topics at a developmentally appropriate level without having to take on the Spark Alpha Explore project. These can be accessed right in our community of practice. The materials, we have quantum mechanics into bite-sized components. We use an engaging hook to capture attention, and then a dual-leveled reading framework that covers quantum computing, sensing, and cryptography. Because we tiered everything into level 1 and level 2 tracks, an 8th grade general science class and a 12th grade engineering track can actually engage with the same exact core quantum concepts at their own readiness levels. Our student data highlights strong engagement. 83% of participants report increased awareness of real-world career pathways, and 76% successfully connected classroom learning to real STEM industries. The qualitative feedback from teachers validates this design. They noted that it creates accessible entry points for all academic levels while forcing rigorous engineering choices like navigating sensor types and boundary conditions to build advanced reasoning skills. Ultimately, teachers agree that this program stands apart because it moves forward with how the world is evolving, bypassing abstract projects to show students exactly how modern advanced technology operates. Ultimately, creating a sustainable quantum-ready workforce requires us to democratize technical literacy early by empowering educators with modular project-based tools like Spark Alpha Explore and Quantum Impact. We move advanced concepts out of university research labs and straight into the hands of the next generation. Thank you so much for your time. The links to our community practice are on the screen, and I look forward to taking any questions you might have.
Thank you very much, Vanessa. It was indeed very inspiring. And I think you've shown that quantum technologies isn't just about advancing the science, but it's also about inspiring curiosity, building awareness, and creating opportunities for students. And the work at Spark Photonics is very inspiring indeed. With that, I think we've reached the end of our presentations. I'd like to extend my sincere thanks to all of you, all of the speakers present here, to give us your view on your expertise and also your perspectives on to what to look forward, and also to the audience for joining us today.